It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Finding Doing Nice Coffee.
Hi guys, welcome to my latest video. Today I'm going to be just talking a little bit about melting points and boiling points in organic molecules. Okay, so hopefully by this time you're a little bit into the organic chemistry topic and you've been able to go through and draw structures and write formulae and go through some of the equations that are typical of organic molecules. But what I'm just going to talk about is the reason why we get these differences in boiling points and melting points across different organic molecules. Okay, so there's a couple of things that you need to bring into account when you're talking about melting points and boiling points. Okay, and the first one is all to do with the bonding. Okay, so when you're talking about bonding, what I'm talking about in particular really is your secondary bonding. Okay, so there's three types of secondary bonding. All right, so there's the hydrogen bonding, which is the strongest, and then there's the dispersion bonding and dipole-dipole bonding as well. So if you need a bit of a recap on that, I suggest you go back and have a look at the video that I put together around those. But it's really key to understand the different types of bonding, right, that will occur between molecules. Now that bonding that will occur will quite often come down to the second point which you need to consider, okay, which is all about the polarity. Okay. So when you're talking and looking at the polarity of the molecule, okay, you really need to have an understanding about what polar functional groups are. Okay, so when we're talking about polar functional groups, we're talking about ones like the hydroxyl functional group. We're talking about ones like the carboxylic acid functional group. Okay, those functional groups that have a net direction of charge, generally they have a very electronegative oxygen or nitrogen in them. So you can have amines as well, which is NH2. Okay, and those polar functional groups, when you have a lot of those in there, all of these can form hydrogen bonds, okay, which are the strongest type of secondary bonds, so that has an impact as well. And then the third one, okay, the third thing you need to consider is the molecular weight, okay. So the molecular weight or molar mass of the substance, okay, determines how many secondary bonds you actually get. So the bigger the molecule, the more secondary bonds you get between the molecules, and so the greater the impact that has upon the melting point and boiling point. Okay, so hopefully you have a bit of an understanding about the difference between a solid, a liquid and a gas. Okay, so if we're talking about a solid, okay, what you normally find is that all the particles are nice and close together like this. Okay, so in a solid, the particles don't move. You've got lots of secondary bonds that are occurring between the particles, okay? Because you have a lot of secondary bonds, you require a lot of energy to break apart those bonds, all right, and to start to spread the molecules apart. But when you supply heat to that, okay, what you do is you obviously then you melt it, so that's where your melting point comes in. So when you supply enough energy to convert it from a solid into a liquid, you've reached the melting point. And in the liquid, what happens is now the molecules are further apart. Okay, so there's still interactions, there's still these secondary interactions that are occurring between the molecules, okay, but they're moving around. So what happens is they're actually forming secondary bonds and then they're breaking secondary bonds and they're moving around. They're not fixed and rigid like this. So there's much fewer secondary bonds within a liquid, which means, all right, that the molecules aren't held together as strongly. If you supply more heat to this, and you supply enough heat to actually break the secondary bond completely apart and get the particle moving fast enough that it can't remake another secondary bond, you get to a gas. And in the gas, the particles are really far apart, okay, and they don't actually form secondary bonds with each other, okay. So that's obviously your boiling point as well. So it's important to understand the difference between how we go from a solid to a gas, okay? And as we increase the temperature, okay, you're supplying more energy to the particles, all right? They start to vibrate, they start to move fast, they start to break those secondary bonds and move apart. As you keep increasing the temperature now from a liquid into a gas, the particles move even faster, the secondary bonds break, and the particles are no longer together in the same space, so they've become a gas. So when you're looking at organic molecules, you need to, as I said, take into account these three parts over here, okay? And primarily, like, your polarity is kind of linked to your bonding as well. That will determine it. So if you have polar functional groups in here, like these ones, you'll get hydrogen bonding, which is the strongest type. So I'm just going to compare a couple of molecules, right, just to be able to go through and, I guess, show you the difference. So what I'm going to do is I'm going to go with ethane, which is C2H6. Okay, now that's an alkane. All right, that's an alkane. It's a very typical hydrocarbon. Okay, there are no polar functional groups in here. This is a non-polar molecule. Okay, so what that means is that this exists as a gas at room temperature, because the type of bonds holding these together are dispersion bonds. All right, we've got a non-polar molecule, so all we've got is hydrogens bonding to other hydrogens. They're very, very weak. It's a relatively small molecule. Okay, C2H6, small molecule. So you don't need a lot of energy to break those secondary bonds. Okay, so if we summarize that, okay, it's got weak dispersion bonds. All right, and it's a small molecule. Okay, which means it has few secondary bonds. Okay, that's why it has a low boiling point and it is a gas at room temperature. Okay, so that's summarizing up your ethane. Okay, but if you then go much bigger, okay, and we look at another organic molecule, so this time we're going to stick with the alkanes and we're going to go here to octane, C8H18. Okay, again it's an alkane. Okay, so it's still going to be non-polar, but this time, okay, quite different. Okay, what's quite different about it, all right, is that it has still weak dispersion bonds. Okay, but all right, it's a large molecule. So what that means is there are lots of secondary bonds. All right, so you've got 18 hydrogens all forming secondary dispersion bonds with other octane molecules. All right, so as a result, it has a higher boiling point, and therefore it is a liquid at room temperature. All right, so just simply increasing the molecular weight here, okay, you can see, so bonding we looked at, all right, polarity didn't come into account, so just by increasing the molecular weight here, you can see we've increased the boiling point, okay. However, if we then compare this ethane here to something that's got a different type of bonding in it, all right, and the molecular weight won't be too dissimilar, let's go with ethanol, so C2H5OH, okay? So this time what we've got, all right, is an alcohol, okay? And this is polar this time, because you have this polar OH group, which I've said over here. The electronegative oxygen there creates a difference in electronegativity between the hydrogen and the oxygen. You can get a very strong secondary bond formed there. Okay, so what we've got is we've got strong hydrogen bonds between the molecules. Okay, it's still a small molecule. Okay, so we don't have any more secondary bonds really in ethanol than we do in ethane. Okay, however, it has a higher boiling point. It's around about like 78 degrees or something like that. So therefore, it's a liquid at room temperature. Okay, the molecular weight isn't that different. The number of secondary bonds isn't that different. However, the polarity of the bonds or the strength of the secondary bonds is quite different. We've got hydrogen bonds versus dispersion bonds. Hydrogen bonds are much stronger, require a lot more energy to break, so to actually separate those ethanol molecules from each other, which is why it's a liquid at room temperature instead. Okay, if we added another OH group onto this, all right, so we made an ethanediol, all right, the boiling point then goes up to about 178 degrees, so it's quite significant the impact that the strength of the bonds has. Okay, so anytime you're dealing with organic molecules, what I suggest is you consider the bonding. All right, does it have hydrogen bonding? Does it have dipole-dipole bonding, or does it have the weakest dispersion bonds? If it's non-polar, pretty much always it will have dispersion bonds, which are the weakest. Okay, then you have a look at the polarity of the molecule. All right, does it have any polar functional groups in it? The alcohols, carboxylic acids, the amines. Okay, amide functional groups are also polar. All right, ester groups cannot form hydrogen bonds. Just be aware of that. So they won't form stronger secondary hydrogen bonds. You'll be able to get some dipole-dipole bonds forming, but not hydrogen. All right, so they have lower boiling points. and then simply look at the molecular weight. Okay, if there's a lot more atoms in there, you have a lot more secondary bonds that can be formed, okay, and therefore your boiling point is higher because you have more energy that's required to break the molecules apart, so hence a higher boiling point. So hopefully this has been helpful for you. Like I said, if you don't have a handle on the types of secondary bonds, go back and have a look at that video, okay? And just encourage you to be able to understand your formulas for your organic molecules. Make sure you know your polar functional groups so you can identify when you're going to have polar hydrogen bonds in your secondary bonds for your molecules, and that will hopefully help you to determine if it's going to have a high or a low boiling point and explain why. Thanks, guys.